Okay, so we started recording now. So let's get started. And we are in the last 2 weeks of this quarter. And so we're going to finish out continuing our linear systems and how to solve these linear systems. And so today we're going to talk specifically about the matrix inverse. And we're going to calculate that by hand with a 2x2 and then a 3x3. And then use that similar process in MATLAB, and then introduce you to the INV function and how to use that for these linear systems that we just barely scratched the surface on last time. And then we'll have a WP on Wednesday. And then on Thursday and Friday, on graphical method. Thursday, I think we're going to do Kramer's rule. On Friday, we may do Kramer's rule on Monday. And then moving into next week, we'll have the final WPA. And then we'll finish up by looking at a process of solving the systems called Gaussian elimination. And so in Gauss elimination, if we had our additional week, the 10th week of the quarter, we would continue in that and start to see some nice, simple ways to solve these linear systems. So as a reminder, these linear systems are a very, very, very common structure that you're going to see in a lot of your classes. Most of engineering really revolves around this linear case, even though non-linear, as I drew that picture last time, our world is just non-linear all over the place. Part of being an engineer and a good engineer is knowing when you can make those assumptions of linearity, and then that allows you to take advantage of a lot of the tools that you learn in these different classes. So with that said, we're just practicing on these linear algebraic equations, okay? There's this linear and linearization isn't related, or isn't limited to, rather, just these linear algebraic cases. Linearization also occurs in differential equations, and whether it's an ordinary differential equation or partial differential equation or just all over the place. And so let's just pull up a small system again. Okay, so let's take, and when I say small system, we can put that in quotes. So small system of equations. And so a small system would have two variables. So our variables would be x1 and x2. So that's something that, in fact, the next lesson that we're going to be visualizing these, where we have 3x1 plus 2x2 is equal to 18. And then let's use negative x1 plus 2x2 is equal to 2. Okay, so we've got these two equations here. We can solve this using the elimination of unknowns. And that's where we would put this into a form where 3x1 plus 2x2 is equal to 18. And then below that, put that same equation. So plus 2x2 from above. And then I want to eliminate my x2 from this equation. So to do that, I would multiply the second row by a -1. And then when I add these rows together, I get 3x1 plus x1. Collecting those terms, I get plus 2x2 minus 2 times x2. And we've eliminated that. And then this is equal to 18 minus 2. So we get that 4x1 plus 0 is equal to 16. And then this gives us our solution, where when we solve for this, x1 is equal to 4. And then we'll plug this back into, this is equation 1, this is equation 2. When we plug this back into equation 1 and then solve for x2, we get 3 times 4 plus 2, x of 2 is equal to 18. And then this gives us that x2 is equal to 3. Okay, so these are things that you've been doing for years, probably since Algebra 2, I think, is probably when you saw most of this, maybe Algebra 1, Algebra 2. And so putting this, but what we want to do here, we're interested in matrix methods. And so as a reminder, we want to put this into matrix form. And in a matrix form, we have an A matrix, an X matrix, and then this is equal to a B matrix. And this is where the A matrix is square, so an n by n. And then our X matrix is an n by 1, so it's a column matrix. And then our B matrix is an n by 1 column matrix. And so we get there, let's write out those steps again. So step 1 is going to be, we write the equations and the book calls it natural form. And so by the natural form, I mean, we're essentially saying it's going to be an invariant coefficient, okay, or constant, multiplied by the variable, okay? So each variable multiplied by a constant. And then we want to identify the unknowns. Okay, so in these equations, you may have all kinds of unknowns, x1, x2, x3. It might be an x and a y and an m or something like that. But you want to write these down. So x1, x2, and on, because that's what's going to form your X matrix, your column matrix. Now you want to isolate those unknowns. So this is where we rearrange and do what you need to do. So it's only a constant. So that constants, all the constants are collected essentially. So for example, if you've got something that's like a x1 plus b x2 minus c x1, then we're now going to have an a minus c x1 plus b x2, right? So we're collecting our coefficients essentially. And then we're going to write that into the matrix form. Okay, and so then the focus of today's lesson is all about, you know, we're taking these systems, we can solve them in a particular way, but we want to solve them by saying, at least today we will, where we've got AX is equal to B. And we know that when I multiply and do a left multiply of A by the A inverse, and I need to left multiply both sides of the equation. Okay, this is the principle. You do the same thing to both sides of the equation. Then this gives us the identity matrix. Okay, and then, so that means we've got X, and then we have A inverse times B. And we are going to be using this to solve for that matrix X. Okay, so that's the key. How do we get our inverse of A and then multiply it by that B vector to obtain our solution for our X matrix? Okay. So let's do that for our small system that we just had. So so for that system, it was 3x1 plus 2x2 is equal to 18. Negative x1 plus 2x2 is equal to 2. So writing that into matrix form, we said it's x1, x2, and then this is equal to 18 and 2, and it's 3, 2, negative 1, 2. All right, so in the AX is equal to B form, our A matrix is equal to 3, 2, negative 1, 2. And then we want to find the inverse of A so that we can left multiply that times B to get our solution. Okay, so then X is equal to A inverse times B. All right, so to find the matrix inverse, we're going to use two different methods, okay? The first method we're going to use is what we're going to use by hand. We'll show you how to do that in MATLAB with the built-in functions that are there, and then we'll just use the INV function in MATLAB. So the definition, so the definition we're going to use is where the matrix inverse is equal to what's called the adjoint of the matrix A divided by the determinant of matrix A. Okay. Has anyone seen this before? Give me a thumbs up if you've ever seen this method of calculating a matrix by hand. Has anyone in here? Okay, we got one person. It's great, sorority. Has anyone ever? Well, let me just ask. Give me a thumbs up if you've calculated a matrix inverse by hand. Like have you ever done that before? Okay, all right. Well, then let's talk about how to calculate a matrix inverse by hand then. And so the adjoint, and I don't want to scare you with these words and this kind of stuff. I mean, the adjoint is a particular type of conjugate, and so this is where the adjoint, and we'll just do ADJ of A is equal to what's called the cofactor of A. So we're going to come up with what a cofactor of a matrix is. You take the cofactor, and then this cofactor of A, you transpose it. Okay, so that's the definition of an adjoint in this case. So we need to then figure out what a cofactor is. So a cofactor, so a cofactor of A is where we're going to get what's called a matrix of minors. Matrix of minors of A. And then we're going to multiply this, and this would be an element-wise multiplication of a checkerboard. That's about the best way I can put it. A checkerboard of pluses and minuses. Okay, and so so let's get into what the matrix of minors is in this case. So the matrix of minors, okay, so to remind us, we've got our A matrix, which is 3, 2, -1, and 2. You've actually been working with a matrix of minors multiple times, and we did it the last time with our determinant, where we would cover up one of the elements, and then, or we would choose an element rather, and then we would cover up the column, and then cover up the associated row with that element. Okay, and then what was left was when we used a 3x3, we had a 2x2 that was left, and then we called that 2x2 a minor. Okay, so a minor is what's left over when you cover up the row and column that's associated with an element in the matrix. And so in that minor, we would then take the determinant, and that's called the determinant of the minor. And then we would just place that, in this case, to get a matrix of minors, we would place that into the matrix. So in this case, with the 2x2, our matrix of minors of A is where we'll cover up our 3, okay? We'll take our 3, we'll cover up the row, cover up the column associated by the 3, and what's left is our 2 that's there. And so the determinant of 2 is 2. And so we would just put a 2 in the position of the element that we covered up. And so then keep on going. So we're going to choose our 2. We're going to cover up our column, cover up our row. We're left with -1. The determinant of -1 is -1. Okay. And then you can see where we're going with this is that we'll choose this element, -1, cover up the column, cover up the row. What's left is the 2. And so that means, whoops, hold on, I think I messed this up, guys. Sorry about that. When we choose our 2, cover up our row, cover up our column, what's left is our -1. So that means our -1 goes here. And then we'll do the same thing. We'll choose this -1, cover up the column, cover up the row, what's left is our 2. And then choosing our 2, cover up our column, cover up our row, what's left is our 3. The determinant of 3 is 3. Okay, so you can see what we've done is we've flipped everything, okay? It's like we flipped it twice. And then we're going to take our matrix of minors, and to get the cofactor of A, we take our matrix of minors, 2, -1, 2, 3, and then we're going to multiply that by plus, minus, minus, plus. So we have a checkerboard of pluses and minuses. And so that makes our cofactor equal to 2, so 2, 1, then -2, and then 3. All right, so that's our cofactor matrix. Then we take our cofactor of A, we're going to take the transpose of this, and then this is our adjoint. So the transpose of our cofactor matrix is, we keep our diagonals the same, and then we flip our -2 and our 1, so we get a 1 and -2. All right, so that's now our adjoint. Now our determinant of A is nice and easy. So our determinant of A is 3 times 2 minus -1 times 2. And we get 6 plus 2, and that's equal to 8. And so we find that our matrix inverse, or inverse of A, is equal to our adjoint, so 2, -2, 1, 3, all divided by the determinant of A, which is 8. And we get the matrix 1/4, -1/4, 1/8, and then 3/8. And so that's one method to be able to take the determinant, to be able to take the inverse of a square matrix, a 2x2. You can also do this with a 3x3, which we'll run through in a second. Okay, so so if we go to MATLAB, we can of course check our solution, where we have A is equal to, we said 3, 2, -1, 2. And then let's check our intermediate steps by looking at the adjoint. So the function is adjoint. So if we do help adjoint, it's going to give us the adjoint of square matrix A. And so you can read more about the adjoint in the documentation. And so if we take the adjoint of A, then we get a 2, -2, 1, and 3. And then by taking the determinant of A, we get 8. So this looks great. And then if we calculated this correctly, A inverse, just assigning it to this variable, will be the adjoint of A divided by the determinant of A. Oops, misspelled that. There we go. Still not getting it. Did I mean? Yes, I did mean that. Ah, I see. I had a capital A. And so, so with this, we get 1/4, -1/4 in the 1, 2 position, 1/8, and then 3/8 in those positions. And if this is correct, then that means that A inverse multiplied by A should give us the identity matrix. So we did get it right, and that's a good sign. Okay. So I want to walk through an example with a 3x3, just so you can see where this is coming from. And I'm going to pick the system that we talked about last time, where we have A is equal to 1, 2, 3, 0, 1, 4, 5, 6, 0. And then remember, we want to find the matrix inverse, where we're getting the adjoint of A divided by the determinant of A. And so we need to come up with the matrix of minors to begin with. So remember, so the adjoint is equal to the cofactor transpose. And this is where the cofactor is equal to that matrix of minors multiplied by the checkerboard of signs. Okay. And so to get the matrix of minors, draw a big matrix so we can do our calculations. And so we're going to cover up the 1, all right, cover up the row and the column that it's in, and then take the determinant of what's left, which is 1, 4, 6, 0. Okay. For our first minor, we're going to choose 2, cover up the row, cover up the column, and then what's left is 0, 4, 5, 0. Take this column, this row, what's left is 0, 1, 5, 6. Take this row, this column, what's left is 2, 3, 6, 0. Then we'll cover up our middle row, middle column, and what's left is 1, 3, 5, 0. And then cover up the middle row, last column, and we got 1, 2, 5, 6. Cover up our first column, last row, and we get 2, 3, 1, 4. Cover up our middle column, last row, we get 1, 0, 3, 4. And then cover up our last column, last row, and what's left is 1, 2, 0, 1. Okay. And so to get our entire matrix of minors, we'll calculate each of these determinants, and I'm just going to write these in instead of working through each of the calculations. Negative 24, negative 20, negative 5, negative 18, negative 15, negative 4, 5, 4, and 1. And so then our cofactor will be our matrix of minors multiplied times our checkerboard of signs. And so cofactor of A will be negative 24, 20, negative 5, negative 18, negative 15, negative 4, 5, 4, 1. And then this is an element-wise multiplication, plus, minus, plus, minus, plus, minus, plus, minus, plus. And then from that we get negative 24, negative 20. I'm going to put that on the next slide so we can see a little better. Negative 24, negative 20, negative 5, 18, negative 15, 4, 5, negative 4, and 1. Then to get the adjoint, we're going to take the transpose of the cofactor, which means we leave our diagonal the same, negative 24, negative 15, 1. And then we put a negative 20 here, 18 here, negative 5, 5, 4, and negative 4. So we flipped around our diagonal. And then coming up with our determinant is actually pretty easy because we've already created our matrix of minors. And so, so that means in our determinant, let's write this original matrix for reference. So our A matrix is equal to 1, 2, 3, 0, 1, 4, 5, 6, 0. And so here where it's going to be our determinant, that's where we choose this element 1. And we're going to multiply it times the determinant of the minor. And so that means we'll just grab this negative 24. So 1 times negative 24. And then it's negative 2 multiplied times its minor of 0, 5, 4, 0, which is 20. and then plus 3, and then its associated determinant of the minor is -5. When we do the algebra, we get 1. And so we get the adjoint of A and the determinant of A. So we get A inverse is equal to -24, 18, 5, 20, -15, -4, -5, 4, and 1. So our inverse is actually equal to the adjoint in this case. And so, so we're solving for x. So to solve for our x1, x2, x3, we would take our A inverse, so -24, 18, 5, 20, -5, -4, -5, 4, and 1. We're going to multiply that by our B matrix from the problem, which is 3, 4, and 1. And then let's go ahead and calculate this. So -1, or x1, x2, and x3 by doing the matrix multiplication. We will get 3 times -24 plus 4 times 18 plus 1 times 5. So 3 times 24 plus 4 times 18 plus 1 times 5 for the first row, or our first value. And then 3 times 20 plus 4 times -15 plus 1 times -4. And then 3 times -5 plus 4 times 4 plus 1 times 1. And then we'll get our solution to be 5, -4, 2. Okay. And so, so what's really nice about this? Let's go to MATLAB. Let's create a new A matrix. And so our A matrix that we just worked with is 1, 2, 3, 0, 1, 4, 5, 6, 0. Let's make sure that's right. 1, 2, 3, 0, 1, 4, and then 5, 6, 0. We've got our A inverse that we'd like to calculate, and that we can calculate using the adjoint of A divided by the determinant of A. And let's check our solution that it gives is -24, 18, 5, 20, -15, -4, 5, 4, and 1. Okay, so hopefully this will work. So A inverse multiplied times A gives us our identity matrix. So 1, 1, 1, and then zeros. And then if we take our A inverse and then we multiply it times the B matrix, which is 5, the next row is 4, the next row is 2, then, oops, got the wrong one. Whoops, excuse me, this should be 3, 4, and 1, rather. There we go. So our B matrix is 3, 4, and 1, the column matrix. And so we get 5, -4, and 2, okay, which is our solution. So, so that's the first way to do this in MATLAB, and it's using this concept of the adjoint. And the adjoint of A is pretty involved to calculate. I mean, at least to calculate by hand, where we're coming up with that matrix of minors, and then we're multiplying it times that checkerboard, and then taking the transpose. So what's nice is MATLAB does have an adjoint function, which does all that work for you. It also has the determinant function, which we've used before, DET. That's also what you programmed for 2x2 and 3x3 matrices. And then we can use the adjoint divided by the determinant to get that inverse. Okay, so on your practice problems, I want you to practice doing that. work these out by hand. I recommend you do them all by hand, just so you've got a good feel for it. And then also check your solutions by doing the adjoint divided by the determinant. Now, the last thing I want to mention is that MATLAB also includes the INV function. And this was one that I mentioned earlier on the just basic matrix calculations. And so the INV is going to compute the inverse of the square matrix X. And when calculating this, it is doing it by a system, I think it says here, by a process called LU decomposition. So it's not even using what we did here. It's using a different method, which is a faster method. It's a more efficient method to calculate that matrix inverse. And so one of the things that we can do with our MATLAB here is that I've got my INV A that we calculated earlier. A, I, and V. So A, I, and V, which we have, which we calculated using the adjoint of A divided by the determinant of A. Okay, and so this itself is actually a slower process than using the INV of A. All right, but you can see we're getting the same answer, and there's some sort of round off that we're seeing. Maybe if we use, let's try format long. Let's see what happens. Let's see if we can see any differences here on the adjoint versus INV of A. Yeah, so you can see here, the first one is using the adjoint method, adjoint divided by the determinant, and the second one is using a method called LU decomposition or LU factorization, which we don't have time to address in this class. It's something that you would take and you would see in probably the next level of numerical methods. We will be dealing with these types of matrices, and you'll be able to see why there are differences here, and also differences in speed that we'll get into just a moment. But these numbers, when moving out to this number of decimal places with this floating point operator, we do get slightly different answers, even though we can legitimately say that they're -24, 18, and 5, and so forth. But they end up not being integers because it is a numerical computation. All right. So one of the things I want to show you though is, and why do one instead of the other? I mean, other than the fact that we have to go through calculating an adjoint over a determinant, it actually comes down to computational speed that really matters. So there's a couple commands here that I want to introduce you to, and it's called tick tock. So what happens is that with tick, you're starting the timer. It's like starting a stopwatch and stopping the stopwatch. So tick starts the stopwatch, tock ends the stopwatch. And so if we do tick tock, and you would want to paste it all in your command window at once, is that it's going to give you an elapsed time. And so the time that we have here, let's grab this again. Okay, is 0.005760 seconds. Okay, so lightning fast in this 3x3 calculation. Now, if we were inverting a much larger matrix, okay, that time is going to get bigger and bigger and bigger. And so there's a factor in which the speed of this or the slowness of it is going to increase with these types of calculations. And so one of the things I'd like to look at here is that tock, by the way, it stores, you can, yeah, well, let me see here. You can actually store the time or the speed that's in there, or you can just grab this in this case with these answers. So in this case, let's compare adjoint divided by determinant with the time of INV. Okay, so by just running this, I'll just paste it in here. And you can see that the adjoint divided by the determinant method gives us 5.813 thousandths of a second. And then the inverse method gives us 1,000th of a second. So the speed savings here, if we put this in a percent difference, are going to be, let's subtract these from each other and then divide them by the mean, the average of them. So mean of these two. And we'll put this in terms of percentage. And so this will be our percent change. So let's do our format, short G again. There we go. So we have, let's see if we've done this, if I've done this correct. You know what? Let me change this to be, let's just divide it by the larger number, 0.05. Okay, so we get a 69% decrease in time. So almost 70% savings in time by using the INV function instead of the adjoint divided by the determinant. So if you can imagine having to make this calculation over and over and over, and so let's say you get a program that's running, an hour, you think it's going to run an hour because it's just a massive program because of how many times you need to calculate this matrix inverse, which hopefully we'll talk about reasons next week why you actually never want to calculate a matrix inverse. That this, you would want to clearly choose the second method because you're going to save 70% of your time, okay, at least in this particular calculation. So for your homework and the practice problems, I want you to calculate this matrix inverse two different ways when you're solving these systems. Calculate it using the adjoint divided by the determinant, okay, which is associated with how we're working it out by hand. Calculate the same solution using INV, the matrix inverse that's built into MATLAB. Right now, this is a black box function, okay? We haven't really discussed how this works, okay? I don't want you to compare the two just by subtracting the amount of time. So how many seconds or how many milliseconds did you save in the calculation using this tick-tock function, okay? And I often will use this tick-tock function when I've got something that's going to run for 30 seconds, 40 seconds, maybe a minute, or even longer. It just helps me get a feel for how long the code needs to crunch to benchmark what I'm doing. And so sometimes, if you're working with someone, you can figure out ways to speed that up if it's just really annoying. Or sometimes you end up with code that wants to crunch and for 20 minutes or so, 15, 20 minutes. And so it's just nice to have an idea if you're going to batch process a lot of things, how long it's going to take you. If I've got several different pieces that I need to run, let's say it takes 20 minutes each and I've got 100 of them, well then I've got an idea about when I press go, I need to walk away from my computer for this amount of time or move it to a server. And so it'll be able to speed up those calculations. So, all right. Hopefully part of this was review for you today. There might be some new things that we're doing here. I see someone in, will we be using MATLAB at all today from Rory? Sorry, I didn't see that earlier. Yes, hopefully you were able to get that, Rory. And so hopefully you'll be able to put these into play with just understanding the matrix inverse, make those comparisons to your hand calculations. Okay, pull back from what we did last time with the determinants, and just we're building our toolbox here to understand our matrices. And then after the WP on Wednesday, we're going to switch gears from this idea of calculating an inverse to calculating the answer for the system itself, instead of having to work through that inverse process, which is clunky. As you can see, it just feels clunky to work through it, but also it introduces, because there's so many calculations, lots of errors that can add on top of each other when in each of these scenarios. All right. What questions come from this. How are we doing on at least following the concepts here? Give me a thumbs up if you're following it pretty well. Okay. Excellent. If you're not, I mean, this will be recorded. And I know we went through those calculations pretty quickly. If you're not comfortable with those matrix calculations, you know, particularly the matrix of minors, you know, where we did all those determinants really quickly, this would be great practice for you, not just for this class. Okay, I want you to know this for the class, and that's nice. I really want you to be able to put it in MATLAB and understand the concepts. But for future courses, you will be taking lots of determinants. You will be potentially inverting matrices. We'll be introducing Cramer's rule later. So if you haven't seen that, that's a way to solve a full system. So, you know, use this as an opportunity to just pause and get more comfortable with matrices. And then also go ahead and solve by hand all the way through the x1, x2, and x3 values for your solution. Because if you're not comfortable with matrix multiplication yet, that'll be good practice for that. All right. Well, with that, hope y'all have a good morning, and we'll see you on Wednesday for the WPA.
Thank you.
Thank you.